All right, guys. Today we're going to look at a question called find good nodes. This is a Leetcode question, and this is the second question in our DFS uh, algorithm pattern playlist. And let's dive right into it. Now, the question says, given a binary tree root, a node X in the tree is named good if in the path from root to X there are no nodes with a value greater than X. Okay, a little ambiguous, but let's say the interviewer gives you this information and this information alone, and you have to decipher the meaning. You have to let them know that you understood it to the best of your ability. And to do that, let's try to define what a good node is, right? Good node. Well, before that, let's see what we need to return. We need to return the number of good nodes in the binary tree. Now, a good node is a node which has no greater node in its path from the root. A little more clear, but it's still not 100% clear. So let's walk through an example. Let's say we are given this binary tree and we are told to return the number of good nodes in this binary tree, right? And so the number of good nodes here would be like, based on our intuition, we would start counting the good nodes by traversing the tree. And we say, okay, 3 is the root node. Now all root nodes are good node, right? Because there are no preceding nodes that sit on top of the root node. So all root nodes are good nodes. That's one more assumption that we have got cleared out. And now let's try to traverse this tree. We say 3 is a root node. So this is a good node. So let's try to say that we have number of good nodes. Let's set it to 0 initially, and we set to 1 because 3 is a good node in itself. Let's get to the second node here. To the left of 3 we have 1. Now the path from root node to this node includes 3 and itself, which is 1. And because 3 is greater than 1, 1 is not a good node. So we do nothing, we add 0 for 1. And then we move towards the left again, because we're trying to exhaust all the nodes in the left subtree first, and we get to 3 again. So we look back in our path and we say all the nodes that were in the path from root node to this node, and then we say all those nodes were 3, 1 and 3 inclusive. Well, was there any node which was greater than this node in the path? No. So we add 1 for 3. And now that we have exhausted all the nodes in the left subtree, let's go to the right subtree. 3, right of 3 is 4. Now all the nodes in the path that led to 4 are just 3 and 4 inclusive. And none of them were greater than 4. So 4 is a good node. So we add 1 for 4. And then we get to the left of 4, right? We get to this node. Now we look back at the path that led us to this node and see all the nodes that were in that path. 3 was in the path, 4 was in the path, 1 inclusive was in the path. Are there any nodes that are greater than 1? Well, yes, 4 is greater than 1. And if we want to look back, we'd also say that 3 is greater than 1. So 1 is not a good node. So we factor in only 0 for 1. And now we look at the very last node, which is to the right of 4. Since we have exhausted the left subtree of 4, we are going to the right subtree of 4. And now we are at 5, looking at all the nodes in the path that led to 5. Those are 3 and 4 and 5 inclusive. Are there any nodes that are greater than 5 before 5 in the path? Well, we are only looking at this path. No. So we add 1. So how many good nodes here? 1, 2, 3. There are 3 good nodes. Amazing. All right. While we were traversing through the tree, there's one common thing that we were always looking for. We were looking for a number which would be greater than our current node in the path. So do we actually have to keep track of all the numbers before a particular node? I would say no. All we would care about is the maximum value node before our current node, right? So if let's say we are at 3, we just need to know if there is a node which is greater than 3 before 3 in the path. And for that, we just need to store the maximum node until this point, right? Because if this node is greater than or equal to the maximum node until this point, then we know this is a good node, right? So we don't have to keep track of all the nodes. We just need to keep track of the maximum node until this point and then check if our current node's value is greater than the maximum node so far, then well, it's a good node. Then we keep track of it. We keep account for it. And let's try it. And now that it's clear, it's a little bit clear, but what we want to do, let's translate our statements into code, right? Let's start with JavaScript function here, and let's call it good node count. And then let's assume that we are given the root node reference of a tree that's been implemented somewhere else. We don't care about it. And well, that's all for now. And this is the function definition given to us. The first thing that we usually do in these situations is we just check if the incoming root node is null or not. So let's do that at the very beginning. Say return. Let's return 0 for now. We don't know the purpose of this return statement, but for now let's just return 0. And we know for sure now the exit condition or the base case of our recursive function has been defined. And let's also define the return statement of our recursive function. We know for sure that we need to return something, right? We need to return count or number of good nodes. That's what we want at the very end for a function to return, right? And what will lead us to the number of good nodes is something that we need to find out. We also know for a fact that we need to traverse the tree no matter what. We need to visit every node at least once. And in order for us to do that, there's a very simple way that we had identified in the previous videos, and that was just to call our function recursively, and every time passing in the left node and then passing in the right node. So this would spawn up a list of function calls that would cover the left subtree, and this would spawn up a list of function calls that would cover the right subtree, right? And now we know for sure these two statements will let us traverse the tree in a root left right fashion. And then once we have traversed everything, we somehow have to calculate the total number of good nodes and then return it, right? So this is the very basic skeleton of our function, recursive function. And now we need to figure out a logic. So let's start with our intuition. Our intuition was to keep track of max value so far, right? And going back to it, just to recap, at any given point, we just need to keep track of the maximum node until this node to classify this one as good or not. So if the max node until this point is still smaller than this node, then it is eventually a good node. And so if you look at our function skeleton here, we don't see a max so far variable holding the max value. So we need a variable here to keep track of the max value in the path. So let's add in a max so far variable. Okay. We name it as we call it, and then we in JavaScript we have a number, and number object has a lot of properties, and I want to set this max so far to the smallest possible negative number that could exist in JavaScript. And so I would say number, which is an object in JavaScript, prototype object, and we would find the properties of it. So if you look here, we would find negative infinity as the smallest possible negative value in JavaScript that could exist. We set it to the smallest possible value, and now in every call we need to create a variable to have the number of good nodes thus far, right? So number of good nodes is a variable, and we set it to 0 because we don't know the number of good nodes so far, right? This is the very beginning of the call. All we know until this line, which is line 25, is that the incoming node is not null. So this is what we need to calculate, right? So for this root node, the number of good nodes below this root node would be the number of good nodes in the left subtree plus the number of root nodes in the right subtree. And so how do we do that, right? We take this variable, right, and then logically we just have to add what our function returns for the left subtree, and then we add what our function returns for the right subtree, and then eventually we return the number of good nodes after calculating it, right? One thing that we are forgetting here is our new function attribute that we had added. Now let's refer to it as parameter, function parameter. This is the second optional parameter that we had passed in. Now this is optional for the external caller, but for any calls within this function, it would be best for us to pass that in. So we will pass max so far. Let's pass it here as well, max so far. But one thing we notice here that max so far has never been set to an appropriate value. And the logical thing to do here is, in every iteration, we just need to update max so far. And the way we would do that is say max so far is max of max so far, or replace it with the roots value if the roots value is greater than max so far, right? And in JavaScript we always have to do math.max, and then eventually return number of good nodes. And well, there's one more condition that we are still missing, and that is to calculate the number of good nodes. This would give us the number of good nodes in the left subtree, but what about this node, right? Do we factor in this node? So check this node to see if we can factor this in. Check the current node to see if it is a good node, because that's the main thing that we want to do in every call, right? So to say if root.val is greater than equal to max so far, then we just consider it as a good node, and then we increment our good node, and that's it. And then we go ahead and calculate number of good nodes to the left of this node and to the right of this node, and once everything's done, we're going to return the number of good nodes. A simple way of writing recursion. And now let's look at the time and space complexity here. The time complexity is going to be big O of, right? Let's see what it's going to be, right? N, where N is the number of nodes in the tree. space complexity again is going to be big O of n, where n is the number of nodes in the tree, i.e., and that is the number of calls, i.e., the size of the recursive call stack. So this was very straightforward. This was a way to use DFS. As you can see, this is DFS that we are doing. We're calling all the left nodes, and then we are calling all the right nodes for every left node, and we eventually trace back to the root node and then return the results. Okay. All right, so this was our question called find good nodes. This is the second question under the DFS pattern. We're going to look at a couple of more interesting and exciting problems that would help us understand DFS better and help us burn DFS into our memories forever and ever to come. All right, thank you guys. See you in the next one. Bye bye.